Let us continue our study of series. Infinite series. We have a sequence, AI, and we want to know if we can add all the terms of that sequence and obtain something that is finite. That is to say, is the series convergent? And it is a very difficult problem. We saw some series. We looked at this sequence here. What is this series? 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. And we established last time that this series converges to a finite number or diverges to infinity.
Diverges.
We did a fancy proof there. It diverges to infinity. This is actually infinite. And how about this one here? What series am I adding here?
1 plus 1 over 1. 1 over 2 squared.
The question is, does this series converge or diverge?
It converges.
And this is the one I'm going to prove to you today, that it converges. And it's not an easy proof. This is called the harmonic series. And you must know that the harmonic series diverges. It's a very important series. And you saw how we proved it. We had those fractions. Special math. How about this one here? What series is that? Let's just keep it too hard now. Well, what's the first term?
3 plus 1 over 2.
4 over
2.
2, and the next one?
7 over 4.
7 over 4, and the next one?
10 over 6.
10 over 6. And the next one?
13 over 8.
And the next one?
16 over 7.
Does this series converge or diverge?
It's like diverges. Diverge.
Who says it converges to some finite number? Who says it diverges to infinity? Who doesn't know? But the answer is it diverges to infinity because the terms of the sequence are not going to 0. That is called the divergence test. What are the terms of the sequence going to?
Infinity.
Huh?
3 over
3 over 2.
Right.
This is where you take off your jacket. You see that as I goes to infinity, the terms go to 3 over 2. So that at the end of the day, you're just adding 3 over 2, 3 over 2, 3 over 2, 3 over 2. And if you keep adding 3 over 2, you will get what?
Infinity.
This is called a divergence test. Huh?
Yeah, right.
Divergence test. of AI. The AI go to 3 over 2, which is not 0. So keep adding that number. You will get infinity. How about this one? Who says that one converges? Who says it diverges? Who doesn't know? The answer is that the geometric sequence with a common ratio of 2/3.
And the in the ratio is less than 1.
So it converges. If you don't understand why this is a geometric sequence, I write down a few terms. What's the first term? 3 times 2/3 to the power 0 is what?
3.
3. And the next one? 3 times 2/3 to the power?
1.
And the next one? 3 times 2/3 to the power? This is where you take off the jacket. Now, this is a geometric sequence with a common ratio less than 1. It must converge to a finite number. Converges by the geometric series test. How about this one? Divergent because
R is
it's a geometric sequence with a common ratio bigger than 1. That is to say, the terms don't go to 0. Here are the terms that are going to 0 because you are multiplying by 2/3 and 2/3 and 2/3 and 2/3 and 2/3. So you can add them all up, provided they go to 0 fast enough. Well, here are the terms that are going to 0, but what is the problem? They're not going to 0 fast enough. So it seems that here, the terms are going to 0 fast enough. I have to prove that to you. Now, this 0 is convergent because the terms are going to 0 fast enough. So the terms are going to 0, you say what? Dang.
Not fast.
Watch. I'm going to prove to you that this series converges. Why? Because the terms are going to 0, so now I have to roll up the sleeves. That means I have to do some serious work. Just like here, the terms go to 0 and I had to do some serious work. Take a look at your notes. So here's my proof that it is a serious proof. That is to say, it involves some serious mathematics. Just like when I prove this. Take a look at your notes. It involves some heavy-duty mathematics. Now, so I'm looking at this sequence here. 1 over 1 squared, plus 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, 1 over 6 squared, 1 over 7 squared. Add them all up. 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4, and add them all up. That is to say, I'm looking at this sequence and I'm finding the series for it. Now, if I'm looking at a sequence, I said you can look at a function and evaluate it at the integers. What function am I looking at here?
1 over x squared.
Indeed. Okay. Now I told you I'm going to prove to you that this thing converges. That is to say, this thing here. 1 over 1 squared plus
1 over 2.
1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared plus 1 over 6 squared plus 1 over 7 squared, and don't stop. I'm going to prove to you that that number is actually less than 2. I don't know what it is, but I know it's certainly less than 2. So, Mr. Breda was correct. I want to look at 1 over x squared. And I evaluate this at the integers. What is this?